I'd like to take this time at the end of Lesson 2 to sort of give my perspective on thinking about atoms and electrons and sort of starting to rationalize um, a model to explain reactivity. And so I think that when people think of chemistry, they tend to think of atoms. And as I've said, atoms are vanishingly small. You have no hope of directly observing them. And so everything that we think about in chemistry, we're going to have to infer properties of very, very small things from what we can see. How very small are we talking? Well, let's have a look at the atom. If this line here on the slide is 1 millimeter across, then an atom would be right about here. And that's just obviously too small to see. Atoms are much, much smaller than a millimeter. So if we zoom in a bit, let's put this in context of, say, the human body. These are human cells. They're about 10 microns across 10 micrometers. So from the millimeter, we've zoomed in about 100 times or so. And next to human cells, which there are billions or approaching trillions in your body of different cells, again, the atom is vanishingly small. It's too small to see stacked up against even the tiniest basic component of the human body. We'll zoom in some more. Assuming these were muscle cells, if we zoom in further, we'll find myoglobin, which is a protein that's involved in storing oxygen for respiration in the muscle cells to produce energy and allow for movement. This is about 5 nanometers across, so 5 billionths of a meter across. Really, really, really tiny scale. And at this scale, we can finally see what most people consider to be the hero of chemistry, which is the atom. And so say this is an oxygen atom. Myoglobin's job is to bind this. So you can see we're dealing with very, very small scales. But even more than that, we say an atom is about an angstrom or so across, but that's a bit misleading, because if you think about all the stuff that's in an atom, atoms are made up of protons, neutrons, and electrons. The vast majority of the mass of the atom is accounted for by the protons and the neutrons, which we know from Rutherford's experiments to be occupying a very small space in a nucleus where the protons and neutrons and all that mass are all together. And the nucleus only occupies about 1/10 trillionth of a percent of what we call the volume of an atom. We say an atom is about an angstrom across, but the nucleus is only about a femtometer across. So what we call the atom seems to be virtually nothing but empty space. If you were to take, say, your own body, and you were able to actually get all the nuclei together and get rid of all the empty space in your atoms, your entire body, all of the matter in your body, would fit comfortably inside one of your red blood cells, and that's all the volume that you would have to occupy. Everything around us is almost entirely empty space, and I think it's kind of important to recognize that in order to start to build a good model of how does chemistry work and what do you need to think of as the driving forces for chemistry. So why aren't atoms smaller? Well, I think the real hero of chemistry isn't just the atom itself, but really the electrons in the atoms. And the electron, we can see, compared to the proton and neutron, has a very, very small mass and a very, very small size or radius. And what happens when you get objects that are very small and very light is that we start to have to be concerned with quantum mechanics, with the idea that we can't really say where is that object as a particular point in space and how quickly is it moving. Its location becomes indeterminate. And so these electrons, which are nominally very light and very tiny, are in fact occupying all at once virtually all of the volume or the space around an atom. And so electrons, despite being light and tiny, because of this property of occupying very large space through quantum mechanical properties that we're going to discuss as we go, The chemical properties of an atom are really the properties of its electrons. The nucleus, particularly the protons in the nucleus, give context to the electrons and sort of define the energy available to the electrons and defines how they're going to behave. So chemistry is all about how happy are electrons. So when we talk in chemistry about stability, what we really mean is chemical stability is really electronic stability. How stable are the electrons? So here's the model that I use in my head to rationalize the simple atomic or elemental properties. We have electrons as the minus signs surrounding a positively charged nucleus. And you know from basic physics that negatively charged particles and positively charged particles will attract one another, and so that's the red arrow here. And you know that the closer they are to one another, the more strongly they will attract one another. So a short arrow represents more energy than a long arrow. Negatively charged particles, you know, will also repel other negatively charged particles. So this is a destabilizing interaction between one electron and the other electrons in the same atom. So the size of a particular atom, exactly where the electrons prefer to lie in the ground state, at what distance from the nucleus, is determined from the balance between how strongly does the nucleus pull on the electron and how strongly do all the other electrons push back on that electron. And so to look at rationalizing the charge stability for small atoms versus large atoms, if you look at a small atom, you can see that the electrons are all quite close to the nucleus and are having strong pull toward the nucleus. The electrons are also quite close to one another and strongly repelling one another, compared to a large atom, where the electrons are further out. The electrons are attracted more weakly to the nucleus. They're also repelling one another more weakly. So it's easiest to rationalize how do we stabilize negative charges. We know that in small atoms, a negative charge is less stable than in a large atom, and that's because if you imagine adding another negatively charged particle into a small atom, it would be quite close to all those other negative charges that are already there. So the repulsive interactions between them will be very large. In a larger atom, if you add another negatively charged particle in, then it is far from the other negatively charged particles, and the extra destabilization that you encounter is not nearly so great. So large atoms will tolerate a negative charge better than small ones. The other way around, the positive charge, is a bit trickier to think about because it's not really so much about the energy of the electron you remove, but what happens to all of the others. So if we imagine from a small atom taking this electron here and yanking it out of the molecule, it'll cost energy equivalent to the attractive energy between that electron and the nucleus, balanced by the repulsive forces. So it costs energy to pull that out, but every other electron in that atom is going to gain energy because its repulsions with that electron will have gone away. So by pulling one electron out, it may cost energy to pull that electron away from the nucleus, but you're going to get some of it paid back by all of the other electrons that now have better, more stabilizing interactions with the nucleus. In a large atom, you pay back less. If you pull out one electron and pay energy to remove it, every other electron in that atom is already far away, and so you will eliminate a relatively weak repulsion. You don't pay back as much of the energy that it costs to yank out that electron. So this is why small atoms are better than large atoms at stabilizing positive charge.